In this video, we're going to take a look at little g, which we have up till this point used in a very specific way, and we want to sort of expand our understanding of it. The background of this is what we already learned about Newton's law of universal gravitation, that there is this gravitational force between any two objects with mass that has to do with how much mass is involved and how far apart they are. This is also true even if the objects aren't simple and spherical, but we'll get more into that later. So we're specifically going to look at how we look at little g and how we use it and how we can figure out what it is, right? We know what it is on the surface of the Earth, kind of using kinematics relationships. You drop things, you measure, but there are ways to predict what it will be at a particular place in orbit or on a different planet. We'll also look at Newton's proof that he did with the moon's orbit to try to explain how this all worked, to support his argument that the universal law of gravitation was valid. So the big distinction here is little g is not the same as big G, right? The big G that we defined in the previous kind of lesson was this universal gravitational constant, 10 to the negative 11th Newton meter squared per kilogram squared. So that one has to do with how strong the gravitational force is between these two masses a distance apart. But little g, of course, is something we're much more familiar with. We use it when we calculate the weight of something, usually on the surface of the Earth. The force of gravity, the weight of an object, is mg, and that's pointing toward the center of the Earth. We've also used it in our free fall or projectile motion calculation when you're talking about the y or the vertical dimension of motion near the surface of the Earth. We accept that in the absence of air resistance or any other forces, we get this sort of free fall scenario. But it also does a couple of other things. For an object that's orbiting in a circle, the centripetal acceleration is the acceleration due to gravity because the centripetal force is the force of gravity. More on that as we go. And then it's also this other thing that I've alluded to very briefly, but it's worth thinking about, is the idea of the gravitational field strength. If instead of thinking of the force of gravity as mg, you think of little g as the force of gravity divided by the mass. Well, if you take out the mass that's there, this just depends on, say, the mass of the Earth and how far you are from it. And that means we could define this gravitational field anywhere in space in reference to the Earth, right? So these lines are field lines, gravitational field lines. They're always pointing inward because gravity is attractive. This lays the groundwork, for some of the stuff we'll do with electricity, because in electrostatics, we also have electric field, but there it could be repulsive or attractive. More on that later. But so this is an idea there that it's the amount of force per kilogram of mass that would be at this point in space. So when we talk about this, we're still all talking about little g, right? We can calculate this on the surface of the Earth, right, which we already kind of know, but we'll redo that calculation. At various distances above the surface of the Earth, where you would be in orbit, and also inside the Earth. What if you were to tunnel down into the Earth? Does this change things? And for what we've talked about with shell theorems, you probably get the sense that things would be a little bit different inside the Earth. So on the surface of the Earth, we can redo this calculation. Why does g equal 9.8 meters per second squared, right? Well, if you take the force of gravity, it's the mass of the object, say you standing on the Earth, times little g. But that's also equal to g mm over r squared. It has to be, right? This is the same force. And if you cancel out the mass of, say, you standing on the Earth and think about, well, what's the acceleration due to gravity where I am standing, or the gravitational field strength where I am standing, it would be g, mass of Earth, divided by r squared. So it depends on the mass of the Earth, but not on m. And that's why it's a constant for everything everywhere on the surface of the Earth, right? And so Newton's theory, right, explains then why everything accelerates at the same rate. Because everything experiences the same, magnitude of gravitational field strength at a particular point, a distance from the center of the Earth. And what about on the surface of the Earth then? Well, does it vary? It does a little bit. The elevation doesn't really matter because going up to the highest mountain, Everest, or the lowest valley on the Earth doesn't really change how far the R value very much because it's the Earth is big. But depending on where you are latitude-wise, it does actually change. So this is not super important, but it's just kind of interesting to think about. We usually approximate it as 9.80 or 9.81, depending on where you are. But you'll see that from the equator, it's a little bit less, 9.78. And when you're at the poles, it's a little bit higher, 9.8, almost 4. So that's kind of what we got there. Then we can think about what if you go up, in space or something like that. You go up into the air. And so when you do that, things are a little bit different again. And what we deal with is the altitude above the surface of the Earth. Now, this is important because altitude is measured up from the surface of the Earth, and that's not the same as being, measured from the center of the Earth. More on that in a second. But you can see that the acceleration drops. But you may notice that even when you're really far above the surface of the Earth, relative speaking to where we are now, like where the space station is, the acceleration due to gravity is still 8.7 meters per second squared. So it's not that much smaller. It's not like it's 0 or anything, which is kind of interesting. We can plot this as a function of distance from the center of the Earth, where radius of the Earth is on there. We're close to 10 on the surface of the Earth, and it falls off like 1 over r squared. When you're infinitely far away from the Earth, we have 0 gravitational field from the Earth. Inside the Earth, using shell theorems, what if we were to just jump in this tunnel, right? This is a question on your questionnaire. Well, what's the force of gravity as a function of your distance from the center of it? That's really the important thing. Well, we kind of have 2 shells. We've got, or the inner sphere, the thing you're still above, and then the stuff that's now above you as you tunnel down. The stuff that's above you doesn't matter, as we've learned from shell theorems. And the stuff that's inside depends on how much mass is below you. And so we need to think about, what is this mass prime? If the thing is of uniform density, the Earth, which is not exactly the case, but it's a reasonable first order approximation, then the mass is just the ratio, of what we had, the volume we have now to the volume we had when it was full. You can do a lot of cancellations, and you end up with a mass that is basically a ratio of where you are to what the Earth's radius is cubed times the mass of the Earth. So from the inner sphere, we then get this particular force of gravity. All right, do some cancellation. G mass of the Earth, mass of you, divided by the radius of the Earth cubed times where you are. So this is interesting. It's actually linear. It goes to 0 when you're at the center, and it's maximum when you're at the surface, right? And it behaves in a way that's negative constant times a distance from the center. This is basically simple harmonic motion. So you will oscillate up and down inside the Earth if you do this. So the period is 2 pi times the square root of m over k. There's that k. You end up with a period of 2 pi times the square root of r Earth cubed divided by g mass Earth. But if you plug in those values, you find that it takes about 84 minutes to oscillate a full time. Would you survive? Absolutely. The acceleration is equal to the force of gravity divided by your mass, and that's only equal to g at the top of the tunnel and 0 at the middle, so you never have a big acceleration, which is the thing that's dangerous. You're going very fast at the middle, but not very big acceleration. So how would you feel? Well, weightless the whole time, because you never have any normal force pushing up on your feet. What else takes 84 minutes? It's the same amount of time it takes to orbit the Earth at essentially low Earth orbit when you're right above the surface of the Earth, which is pretty cool. So we can kind of put this all together into a plot, which looks like this. We've got the force of gravity. We've got little g now, and we can say it's linear. It increases up to 9.8 when you're at the surface of the Earth, and then it goes like 1 over r squared once you leave. So that's it. A couple of references. You can look at these if you want to see a few more examples.